this question, we're given a linear map T from R3 to R4. So that means T takes in vectors from R3 and gives you vectors from R4. And we're also told what T does to the standard basis vectors from R3. We're told that T of the first standard basis vector is this thing, T of the second standard basis vector is that, and so on. Now we're asked to find T of a fourth point. Well, turns out we have enough information to say what T of any point is. The reason for that is that any vector can be expressed as a linear combination of these three vectors we were told about. This question is particularly easy because we can express now 2, -1, 4 as a simple linear combination of these three vectors. Since 2, -1, 4 is just equal to twice the first vector plus, let's see, -1 times the next vector, 0, 1, 0, plus 4 times the third vector. Then we can apply T to both sides of this equation. So T of now 2, -1, 4 is equal to T of this side. So that's 2 of 1, 0, 0 minus 1 of 0, 1, 0 plus 4 of 0, 0, 1. Now I'm going to use the fact that T is linear. I'm going to use the addition condition first to make this T applied to a sum of vectors into a sum of T applied to the individual vectors. That is to say, this is T of 2, 1, 0, 0 plus T of -0, 1, 0 plus T of 4, 0, 0, 1. And now I'm going to use the scalar multiplication property of T to bring these scalars outside. So this is 2T of 1, 0, 0 minus T of 0, 1, 0 plus 4 times T of 0, 0, 1. And I know what T does to the first standard basis vector. That's just the four-dimensional vector 1, 2, 3, 4. So I can finally write this as twice 1, 2, 3, 4. And I know what T does to the second standard basis vector. It sends it to -3, 0, 1, 4. And I know what T does to the third standard basis vector. That's 4, 0, -5, 6. And all up, this is 2 plus 3, which is 5, plus 16, which is 21, 4, 4, 6, minus 1 is 5, minus 20 is -15, and 8 minus 4 is 4, plus 24 is 28. Behold, we are able to determine what T did to a point based only on the information of what T did to three specially chosen points and the fact that T was linear. Now let's look at this property of linearity a different way. We're given a function. It again maps from R3 to R4. This time we're not told if it's linear, so we don't know at this stage if this function T is linear. We're told, however, 4 function values instead of 3. We're told what T does again to the standard basis vectors from R3, and we're told what T does to a fourth vector. It turns out that no linear map can take all these function values simultaneously. And our approach to proving this is very similar to what we did in the previous slide. We're going to start by assuming T is linear. If we assume T is linear, then it is completely determined by these first 3 function values. we're going to then discover what t should be doing, a linear t should be doing to the vector 1, negative 3, 1. So let's proceed. We will start by contradiction. Assume t is linear. And we're interested in what t does to 1, negative 3, 1. Since the vector 1, negative 3, 1 is equal to the vectors 1, 0, 0, minus 3 times 0, 1, 0, plus 0, 0, 1, I can apply t to both sides of this equation. T of 1, negative 3, 1 is equal to, I'll use the linearity of t now to just write this as t of 1, 0, 0 minus 3 of t 0, 1, 0 plus t of 0, 0, 1, which is therefore equal to, well, I know what t does to this vector. That's going to be 1, 2, 3, 4 minus 3 times whatever t did to the second vector, which is negative 3, 0, 1, 4, plus what t does to the third standard basis vector, which is send it to 4, 0, negative 5, 6. And I add these all up and I get 1 plus 9 is 10, 14, 2, 3 minus 3 minus 5 is minus 5, and 4 minus 12 is negative 8, plus 6 is 14. So a linear t would have sent the vector 1, negative 3, 1 to the vector 14, 2, negative 5, 14, which is not that vector over there. 2, 4, 3, 1. This contradiction shows us that our assumption that t was linear must be incorrect. So t is not linear.